the essential question today was, how does Newton's first law of motion relate to the learning objectives of kinematics, non-accelerated motion? Remember, in kinematics, we studied both accelerated and non-accelerated motion. All right, and then I've listed, or I've stated Newton's first law here, as I mentioned earlier. Objects move at constant velocity, which means they're not accelerating, unless a resultant force acts. When that resultant force acts, they do accelerate, right, according to Newton's second law. And so, like, one law leads to the other one. Sometimes it's called the law of inertia. As Bill Nye famously said, inertia is a property of matter. Okay, it's the amount of matter in a substance. It's an intrinsic property of a substance, right? Like the amount of atoms that build it up. It's intrinsic to it. It doesn't matter what gravity field you're in. So when we think about like the weight equation, the weight equation there, okay, weight equals mg. All right, and so mass is the intrinsic thing, but the weight has to do with the gravity field, right? That's doesn't seem silly at all. Above my head, I have an alien spaceship wearing a face shield. Regular sport. Any questions on Newton's first law? We're going to try to kind of go through each of the learning objectives, and then, you know, by the end of class, maybe be able to put some thoughts to paper. How does this law of motion relate to these learning objectives? Okay. And again, it really has to do with the first clause there, just the constant velocity piece. Like, forget about acceleration right now. We began by studying non-accelerated motion. All right, so let's try to center this as best we can. All right, define displacement, speed, and velocity. If we think about this first learning objective, they sort of give us the foundation upon which we build all the rest of the physics. So let's make sure that we just have good textbook definitions in mind. Displacement. We use the letter S for that, right? And so we'll define it as a vector quantity defined as net change in position measured in meters. All right, and so if this were like a paper 2 question and it said define displacement, you could just say something like net change in position. But as we study, we want to kind of remind ourselves which quantities are vectors and scalars and what are the SI units we measure them in, because base units is such an important idea and vectors and scalars is such a foundational idea that you will have questions that will say, like, categorize the following quantities as either vector or scalar. And if you get used to defining everything as, oh, this is a vector quantity, this is a scalar quantity, it not only reminds you that everything we study is either a vector or a scalar, so that's why it's so foundational, but it also will sort of give you, you know, sort of the answers to those specific questions. Like, oh, okay, displacement, that goes under this category of vector quantities. Speed, okay, is a scalar quantity, right? So we have speed here, scalar quantity, defined as distance per time. And you can write out per, or you can, you know, sort of use that. And so speed is distance per time. Speed is distance per time. Measured in meters per second. All right, meters of distance, seconds of time. Remember, distance is a scalar quantity, and so you get the scalar speed when you take the scalar distance divided by time. Displacement is the vector, and so velocity, the last thing we need to define here, is the sort of corresponding vector to speed. So it's like displacement is to velocity as distance is to speed. Right? That's kind of like an analogy. So velocity we'll use the letter U or V for that. So remember, once we get to acceleration, we're changing our velocity. So we need sort of some nomenclature to, you know, how do we state initial and final? So we use U and V, but just sort of in general V. So velocity V is a vector. Quantity defined as displacement, as the rate of change of displacement. If anything is a rate of change, like it's per time, you kind of want to define it like that, okay? A vector quantity defined as the rate of change of displacement, that is to say, V equals S over T, okay? Measured in meters per second. And so there you go. Displacement, speed, velocity. Define them. It just is that straightforward. Like you just have to have textbook definitions. You got to be able to recall them. You maybe make flashcards, do something for yourself so that if you had a question about, you know, one of these definitions, and I think we've seen them before on, you know, like go through the previous quizzes where it's just like define displacement, define acceleration, right? I know we're not defining acceleration here, but those are questions that we've seen before. Draw and interpret displacement time graphs, moving right along to my left and in-person students right. All right, displacement time graphs. We're plotting displacement in meters against time in seconds. It could be like this, okay? We've got a curved line, which would indicate a changing slope, okay? And so the key interpretive idea, okay, with displacement time graphs is that slope gives velocity. The slope of a displacement time graph gives the velocity. So a changing slope is a changing velocity in the interpretation of a curved line then, right? A curved line is one where the velocity is changing, right? Like all the slopes are changing. That's evidence of acceleration. Like if somebody started at rest and then there was a ready, set, go, and then they accelerated up to some top speed, like in a travel of 36.6 meters, okay? The slope here, this is a constant slope. And so this would be like, you know, somebody's sort of reached this speed. So here they're accelerating up to it. Now they've reached that speed. And then the slope, again, they kind of decelerate because they're tired. And then they just remain at rest because they've traversed 36.6 meters in such a record time. Okay. And so I think my delta T yesterday on my 36.6 meter dash was like 6.32 seconds. And then second block, we went out there because the air was still broken. So we went out for a physics field day in second block, and there were students there running like 5.2, 4.97. I'm like, give me, you know, that's a missed time, you know, 4.97. But you know, maybe. Yeah, I said it. It's on. It's there. It's public record. Okay. I want to see it done again. I want to see it replicated, and I want to be the timer. Okay, 6.32 I think stands as probably the record for the day. And these we could probably discard as spurious data points, right? Spurious data points. That's a little bit of trash talk, you know, in the science lab, talking about spurious data points. All right, so this, okay, I'm sorry. I'm jumping over here from draw and interpret displacement time graphs because wouldn't you know we got some displacement time data here. This is empirical data collected ourselves, not myself, as I mentioned earlier. So, you know, trust it as much as you want to here. 9.15 meters, that's 10 yards. 18.3 meters, that's 20 yards. 27.5 meters is 30 yards, and a 36.6 meter travel is a 40-yard dash. Okay, well, travel, right? People can travel however they want to. This person dashed it. This person, you can see that their time for the 10-yard mark was like 2 seconds higher than this person's entire dash. And so this was a leisurely constitutional in the morning, just kind of walking along there. And, you know, less than half a minute. So it's tough to really say, can I walk the slowest? Like always moving forward, but as slow as possible. It's like, I'll race you. And you have to keep moving. Like you can't stop. Okay, you have to keep moving, but at a very slow constant velocity. It's really tough. Okay, it's tough to do. And so we could have a race of like who can cross the slowest. And if you ever stop, you're out. Okay, who's the slowest one? That could be a fun, you know, physics field day. Another event, maybe for another year. All right, your lab work this week was to plot either your own data, plot this data. You could plot both of these sets of data on the same plot and sort of observe. One would go, come on back over here, guys. One would go kind of like this, and one would go kind of like that, right? And again, it would emphasize the idea that the gradient is the velocity for a displacement time graph, and a steeper line, a steeper slope is faster, right? Higher slope, so this person went 40 yards in 5.2 seconds. This person went the same 40 yards eventually, but it took them like 24 seconds to do that, right? So again, it's kind of visualizing, yeah, this one took a lot longer, you know, to cover the same distance. This one did it in a shorter amount of time. A horizontal line, the slope is 0, and that indicates at rest. So somebody who like crosses the finish line and then just sort of takes a break for a few seconds to catch their breath there. You know, it's like somebody that did this, but then I think I like ran back, right? Like that. Because I ended up going sort of back to the starting line. And again, that's what we would say. We'd say, okay, well, this is a negative slope. What's a negative slope mean? Well, it means we're going in the opposite direction, right? Because displacement is a vector, right? So there's lots of interpretations. Curved lines mean acceleration, constant slopes, velocity. Slope of 0 means 0 meters per second of velocity, or rest, right? We're at rest, sort of this distance away. You may recall, what is the moral of this graph? And we can plot a fable like the tortoise and the hare on a displacement time graph. See that entire story and criticize, you know, the hare for, you know, taking a nap when he was so close to the finish line. Then we lose the moral. Slow and steady wins the race. Well, or like sprinting to the finish line will also win the race according to this data. But you know, different conclusion. Describe laboratory methods for determining speed. Okay. Speed, you may recall, is distance divided by time. We defined it just a moment ago. In order to determine speed, we need to measure distance, we need to measure time, and we need to take their ratio. So one way to do it. So we'll say rulers, calipers, tape measure, right? Like a 40-yard marker, right? So some way to measure distance. Stopwatches. Photo gates. A photo gate is a timer, right? It's just a very accurate way to measure time. Stopwatches, you know, there's human error, but we can still get, you know, pretty reasonable conclusions there. So you need some way to measure distance, some way to measure time, and then take their ratio. That's how we determine speed. And we've seen sort of more high-tech ways of doing that. You may recall in the drop lab, we're dropping a marble through a photo gate. We launch a marble through a photo gate when we wanted to know the initial velocity for our projectiles. And so there we're sort of using the caliper to measure the distance of the marble, and then as it breaks the photo gate, right, it's recording the time. And so think about being able to sort of explain an experiment to determine the speed of something, whether it's going out to the field and saying we're going to run this distance and we're going to time it, right? Very, very straightforward, very kind of, you know, easy to do, to something that requires a little bit more precision. Like I'm dropping a marble through a photo gate because I want to sort of use the data to calculate the acceleration due to gravity, which was lab work from a couple weeks back. So, I mean, that's really what it comes down to for determining speed. So, well, I'd use a speedometer. Couldn't I do that? Couldn't I just use like a radar gun? The police officer, you know, sort of checks somebody's speed with a speedometer. A speedometer has clever electronics to measure these things and then take the ratio like within the electronics. Okay, so it's sort of just doing that within the electronics. We have about 7 minutes left. We're on to the final learning objective belonging to non-accelerated motion, where right away we were introduced to this idea of vector addition. Add 2 or more vectors. Let's kind of go over those rules, remind ourselves of the importance of that, and how often we've really had to do that throughout the year. Thinking about Newton's first law, it's really about forces, right? Newton's laws are about forces, dynamics. The force is a vector. But we don't sort of start with that idea. So vector addition. If we've got some vector A, and we add some vector B, the rule is, there's really 2 ways to do it, okay? Place vectors as the tail, connect the tail of the first vector to the head of the last vector. This is the resultant. And now we want to kind of think about consistency in our academic language. If I'm thinking about Newton's first law as, hey, objects just go with constant velocity, unless a resultant force acts upon them, okay? And here we're defining the sum as the resultant, right? The vector sum is the resultant. This is the resultant. So vector sum. And that kind of sets us up for Newton's second law. The sum of the forces equals mass times acceleration. We employed it a moment ago for our tension problem, right? So we had the weight and the force required to accelerate our 1.5 kilogram block, 3.4 meters per second. All right. So for this problem here, A plus B equals, I would, on my vector A, and I put my vector B head to tail with it, and my resultant C would be that, right? So it'd be a vector that would go straight to the right because I went up and to the right, I went down and to the right, so I really just went to the right, okay? The other strategy, okay, the other way to add vectors is to put them tail to tail. And then you sort of connect the diagonal, okay? So like if you, were to like finish the quadrilateral, okay, it would be the diagonal. So it's like you're really drawing tail to tail, and then you're sort of making two sides of a quadrilateral. You can kind of finish, and then the diagonal is the same thing. So you see how either way we do it, we get a vector that goes to the right. I kind of prefer this method, head to tail, but sometimes we're considering like an object, like a block, and it's easier to kind of think about how all the forces are acting on it. So remember, like we could translate a vector in space. So we can say, well, this vector is acting on it, but I want to draw it over here so I can see what the net force is on it. So sometimes students prefer this tail-to-tail method because we can kind of see where all the forces are acting on the object, like at the tail, right? So if I said, here's two forces acting on this object here, it's harder to sort of visualize like this force is acting on it. Because like that force plus this force means this is the total force, the result, right? So sometimes it's easier to see the resultant force C by showing the two, forces acting on it like this and summing them with this strategy, okay? So whatever you prefer. Two different ways to add vectors. And so let's say two ways. This is way number one. Method number two. Place vectors tail to tail. Construct quadrilateral, four-sided polygon. The diagonal is the result. So either way, right? We're trying to sum vectors. We're adding, use vector addition to add two or more vectors. And we could use the head to tail method, connect the tail of the first to the head of the last. We could use the tail to tail parallelogram method, and the diagonal is the result. What about adding negatives? That's a type of addition, right? We can add negatives or subtraction, vector subtraction, okay? That's sort of embedded within this, okay? And we haven't really talked about resolving these vectors, but that's another way that we talked about how we can add them. We could say, well, this vector A has components AX and AY, and this vector B has components BY and BX. And another way to calculate this would be to resolve each vector, add the X components, add the Y components, give us, sort of legs of that right triangle, and then use Pythagoras' theorem to calculate it. So sometimes we have to sort of, go all the way into resolution of vectors, and then Pythagoras' theorem. In the final moments of class here, let me just sort of remind ourselves that for this problem here, A minus B, if we were to do A minus B, okay, what would that equal? We'd have our vector A, and we'd still put vector B head to tail with it, but instead of writing B, we draw negative B, okay? So here you can see if this is B, the negative B would just go the opposite way, all right? So we put it head to tail, but it would go this way. And now the difference between A and B is this result, right? Still connect the head of the tail of the first to the head of the last. So negative B is just the one that's reflected, right? Because the opposite direction, we know negative is the opposite direction. That's the convention we've adopted, the sign convention we adopt when we do our vector math. And that concludes our chapter 1 review for non-accelerated motion. Have a good day, everybody.